to scale. This is for the along the source and drain direction. Of course, then in the other direction you may have the metal wires for the routing. So the metal 1's pitch, first metal, determines the density of the cell. So if you look at that, if you use the gate pitch, multiply the metal pitch as your metric for the scaling, then from generation to generation, it scales well. So here is the Intel's data from 45 nanometer, 32, 22, and this 14, even to 10 nanometer node. If you use this gate pitch multiplied by the metal pitch, that is the area, like unit cell area. That scales well, follows that almost half per generation. That's the Moore's law, essentially. So here, this graph on the right also shows this trend. And here, this is this one is printed gate length. This is 130 nanometer node, and this is the 22 nanometer node. So from 130 nanometer down to 22 nanometer, you can read the scale. The physical, let's say the printed gate length does not scale too much, but the contact gate pitch, this one, and the metal 1 pitch, this one, scales significantly from 130 nanometer down to 22 nanometer. So what is really scaling? If you draw the transistors layout, not layout, let's say cross section. If you draw the transistor like this, gate, source, and drain. So this is the contact for the source, contact for the drain. So the printed gate length does not scale too much these days. But from the contact to contact, this one is scaling. So that means what? So we have the spacer between the contact, let's say source and the gate, and the source, drain, and the gate. So that means really the spacer's distance and also the contact itself is scaling. So that's the key for the scaling.
So I'm assuming they're not close enough to cause any like parasitic capacitances or anything.
So that's a good point. So as you scale the spacer, actually your parasitic capacitance goes up, right? So but you have to design a circuit to, compensate for that, because still you need the density. You want to make it small, but that's the overhead or penalty you have to pay for. So here I think this is most important conclusion I want to pay attention to. What is really scaling is the pitch for the contact gates or the metal 1 wires, not the physical or printed gate length. So if you follow this kind of scaling rule by the contact gate pitch, and if you plot the S1 cell area from Intel's data, I think. So from 180 nanometer down to 22 nanometer, if you look at the S1 cell area, it follows the Moore's law, about half of the area per generation, and each generation is about 2 years. This is till 22 nanometer. I think if you look at Intel's latest data for 14 nanometer and 10 nanometer, this scaling trend is still going on. This is because, again, this contact gate pitch here scales 0.7x per generation. So this is scaling, and on the right hand side we have a table. This is Intel's 22 nanometer design rule. And this is a FinFET technology. So it defines what is a fin pitch. We're going to discuss that in more details later when we really see the FinFET layout. And the fin pitch and the contact gate pitch is like 90 nanometer. So roughly, and metal one is also 90 nanometer. So as you will see that later when we talk about the SRAM's layout, you will see that the metal one pitch is roughly the same as the contact gate pitch, and is roughly the same as 4F. If you still think the F is this symbol technology node. Because 4 times 22 is 88, it's roughly 90 nanometer. So you will see that the metal one pitch, contact gate pitch, roughly 4F, 4 times the symbol technology node. But you know that technology node does not mean anything in the real physical dimensions.
Why does the pitch go down for metal 2 and metal 3, but then continue to go up?
So that's a good question. I don't know. This is Intel's design. But I would say typically, below metal 4, that's local interconnect. So roughly they will have similar pitch. And the metal 5 to metal 8 is like intermediate metals. And above metal 8, then that's a global wires. So you see the pitch increases in general as you go up the metal layers. Okay, so any other questions? So this is for the logic. Then let's look at the memory, like DRAM and flash. So in this case, the technology node, F, really means the smallest feature size in the physical dimension. Because DRAM and flash, as we discussed, they are different than the logic manufacturing process. So, for example, TSMC will not fabricate DRAM or flash because TSMC is only for the logic fabrication. So there are different fabs, different manufacturing sites. So the processes are very different. So DRAM and flash, in this case, F really means the smallest feature size. For example, as we defined earlier, in this layout, the F really means this half pitch of this metal, let's say the gate or the metal one. And if you look at the scaling of the DRAM flash, so I think the pink one is the flash. This is the flash, and this one is DRAM. So below 40 nanometer, around here, the flash outpaces the DRAM scaling. So today, flash is the smallest device. I mean, the industry is making. So smaller than the DRAM, smaller than the logic transistor. If you look at the printed gate length of the flash transistors gate length, it's smaller than the logic. And flash is about, if it's 2D, I think today is like 12 nanometer or so. 12 or 13 nanometer. But as we discussed, as we will discuss, industry stopped from 2D scaling for the flash, roughly like 13 nanometer, 14 nanometer, then industry switched to the 3D NAND flash. So, but still, this 14 nanometer is this printed gate length is still the smallest today, smaller than the DRAM, smaller than the logic for the two-dimensional flash. So the 3D NAND is introduced around like 15 and 16, and then after a year, the industry switched to the 3D. So this will not happen. This two-dimensional transistors printed gate length will not be smaller than 10 nanometer. Because as we discussed, the electrons wavelength is like 13 nanometer. So.
Excuse me, Professor. Why the flash gate length can
really scaled down to 12 nanometer, but the logic gate length is still tens of nanometers.
So there are different, let's say, different design specs you want to meet. So for the flash, the speed is not the priority. So you can use thicker gate oxide thickness. So you can make the source and drain closer, but the gate oxide is a bit thicker, so still you can have some good characteristics because the speed is not concerned for the flash. But for the logic transistor, you have to make a thin, very thin gate oxide. In that case, if your source and drain also very close, then it will not work.
So can I explain sorry.
Yeah, go ahead.
As like the student just said, because the parasitic and the delay, so logic cannot go last one. The logic gate.
That may be the factors, but may not be the critical ones, I think. So it's not a simple story there. But because the application is different, your specs are different. So flash, as I think talked about in the last lectures, for the memory industry, what is number one in the, let's say, all the specs, all the metrics to evaluate your process or technology? Density, cost, okay, is number one for the memory industry. So that's why they really want to scale. They can sacrifice some other, properties of the transistor. But the logic, you cannot do that. Okay, so that's good discussion. And then let's look at the industry. Okay, so this is just for your information. It's not very technical. So if you look at our semiconductor industry, and I think this is 17, the total market, global, is like 330 billion 1 year. And out of this 330, about 80 billion related to the memory. But here the memory, we only say the memory is DRAM or flash. Okay. Because SRAM is embedded on the processor, you cannot really divide that into SRAM, right? So because it's part of the processor.
So TSMC still does SRAM, right?
Yes, because it's part of the logic, it's part of the processor. Yeah. So it's embedded. So here this memory is a standalone memory. Standalone memory. That means DRAM or flash. So within this 80 billion, so basically DRAM and flash. There are some niche applications, even standalone SRAM, but this is not a big market. Or standalone low flash. So really this 80 billion means the DRAM and the NAND flash, because those two combined will be 95% of the 80 billion. And if you look at the industry companies, there are different business models. And as we discussed, the foundry, like TSMC, just does the manufacturing for the logic, or let's say embedded memories, including SRAM. And similarly in Global Foundry or UMC. But TSMC occupies more than half of the market share, I think, these days. And fabless, the design house, only do the circuit design and send the GDS files to the foundry for the manufacturing. And you can name those companies like Qualcomm and so on. And nowadays, NVIDIA is popular because of GPU. And then the third model is this integrated device manufacturing, like IDM. So that means that Intel and Samsung, they can do everything, including both the design and the manufacturing. So they are integrated. And then there are some specialized memory companies here. And Samsung, of course, Samsung has its own foundry. It can do logic. But Samsung's major business is actually memory. And Samsung is number one in the DRAM and number one in the NAND flash in terms of market share. And then the SanDisk now is part of Western Digital. I think last year or 2 years ago, this consolidation happened. And then SanDisk and Toshiba, they co-developed the NAND flash. They are kind of partner in terms of the R&D. And then SK Hynix, I think is number 2 in those DRAM or the flash. It's also a Korean company. And then Micron is doing DRAM, and Micron and Intel co-developed the NAND flash and the recent 3D Point. So basically this is the industry these days. And then let's look at some of the historical trend for the industry. So I like to see this kind of table every year. So this is the ranking in terms of the revenue for the top 20 or top 25 semiconductor. And here this is back in 2006. And at that time, Intel number 1, Samsung number 2, still TI, Texas Instruments is still there. And the ST, the ST Microelectronics, is a European company in Italy and France. So TSMC is number 7 at that time. And those are the rest companies. I don't want to name each of them. So, but I just want to show the trend. So now it's 2010. Okay. Still Intel is number 1, Samsung is number 2. Now TSMC jumped to number 4. You see the rise of the foundry model. And TI dropped to number 5. And now you can see some of the memory companies there, like Hynix, SK Hynix, and Micron. And that time you see Qualcomm for the first time jumped to number 10. And then this is 2014. Still Intel number 1, Samsung number 2. Now TSMC becomes number 3, and Qualcomm becomes number 4. This is because you know the smartphone business. Qualcomm jumped to number 4. And in that year, Micron acquired the Epida, which is one Japanese memory company. So they merged. So Micron becomes number 5, and number 6 is SK Hynix, another pure memory company. So Samsung here mostly is due to the memory business. And this is 2016, still similar. Intel, Samsung, TSMC, and Qualcomm. And this is the latest data from last year. So some changes, I think. First, Samsung become number 1. Intel dropped to number 2 because Intel, I don't know what they are doing these days. Their process delayed, you know. So then you see the memory company really revived. Like number 3 now is the SK Hynix, and number 5 is Micron, and Toshiba becomes purely Toshiba memory because Toshiba only has memory these days. And SanDisk and Western Digital skier. As you can see here, and the Qualcomm dropped because you know the smartphone business, you know, saturates. And you see Nvidia first time jump to number 10 because of the GPU business, right? That's machine learning stuff. So as you can see from this ranking, you can see the industry's involvement in the past 10 years. So to summarize here, CMOS scaling, the small knob by 0.7x in the dimension, or let's say 0.5x in the area per every 2 years. So this will become more challenging in the next few years. The scaling is still there, I think, from generation to generation, but it may take a longer time. previously every 2 years, now maybe 3 or 4 years. But once you scale from one generation to another generation, you still achieve that density improvement by 2 factor of 2 due to the scaling of that pitch. So ITRS is a projection, and the technology node, as I discussed, is more like a symbol for logic transistors. This can be varied by different companies. And that means this technology node does not correlate to the half pitch of metal 1 or the physical phase length. So those numbers can vary. Now it becomes just a symbol. But what really determines the density of the transistor is the contact gate pitch. And this one is still scaling well. And for the memory, like DRAM or flash, the technology nodes really means for the smallest feature size in this case. And also from the ranking in the past 10 years, as you can see that the memory market is becoming more and more important. And many top 10 vendors, you can see here, many of them are memory vendors. This is because memory becomes more and more important in the ecosystem of this semiconductor. So that's it for this lecture. Any questions? I mean for the lecture 2, not for today's class. All right, so let's